Welcome, everybody, and thank you so much for joining us today. This is part of the Proto-OKN webinar series, and we're super excited. Oh, I'm Florence Hudson. I'm part of the Educate team. I'm just representing one of 5 people and many others on the team. And we're super excited to have Jeff Jonas and Paco Nathan join us today. So a little bit about what we're going to talk about today. So Jeff is going to discuss AI for entity resolution, and Paco will present the role of entity resolution in entity resolved knowledge graphs in RAG. Jeff is founder and CEO of Senzing, is a data scientist and creator of entity resolution systems, and has been working on this for decades. He was at IBM, he's done a bunch of wonderful things. Paco is the principal developer relations engineer at Senzing, and he's a prominent data scientist and innovator and has decades of experience too. So we are so lucky to have them with us today, and we can't wait to hear all about this. So once again, Jeff and Paco, thank you, and take it away.
All right, thank you. Paco and I have assembled some very tailored charts that maybe this is one of a kind little show that we've prepared. And we're going to maybe present for 45-ish minutes, and then we'll have 15 minutes for Q&A. I thought I would just start with the way we define entity resolution these days, and it's recognizing when two records are the same despite having been described differently. Look at these two records and you can just see there's a lot of little differences. Conversely, recognizing when records are not the same entity despite having been described similarly. These two records here are almost exactly the same except for the one letter S and the J. Wow, what a difference one letter makes, and in which position. And to do really good entity resolution, as we have come to learn, is you have to be able to track the relationships between entities, which means graph it and network it to produce better quality entity resolution results. Okay, with that, I thought what would be fun today and rather unique in the way I talk about what we do at Senzing is I'm just going to start in the beginning and tell the journey of some of the more important entity resolution projects that we've done. What problems were we solving? What did we learn? So I'm going to start with, I know it makes me old, I can't help that, but we're going to start with the first entity resolution project that my systems research and development company did in the 80s for a collection agency. It was actually part of TransUnion, the credit bureau. And attached to them are these collection agencies, and collection agencies get bad debt. Your check bounced, you didn't pay this bill. And so they're assembling bad debt. And what they don't want to do is have to send 5 notices or make 5 phone calls. And it was actually called debtor matching. And when you're trying to solve this problem, each collection agency has hundreds of different organizations that are sending them different files of different structures. There's millions of collection records, individual debts. There's inconsistent attributes. This data source gets a driver's license and a social. This data source only gets a name and an address and a phone. They're all represented different because it's hundreds of different companies about how they want to collect and represent dates of births, for example. And then some people don't really want to be found and have anything find their credit file, so they're using their middle name and they're changing 1 digit in their social security number. And so when we showed up to automate and make this process paperless, I want you to imagine this as they had, this was a white card, but this was a debt for power and PG&E, power and gas, and here's Sam's Auto Parts, and here's Melody Music, and there's 3 debts, and they would put it into a yellow packet, and on the cover of the packet, they would put all of the names, date of births, addresses, phones on the cover of it. And so, lucky for me, I thought that's really the way it should be. And so what would happen was when a new individual debt shows up from a hospital, you would try to figure out what packet it belonged in by comparing it to the cover of the packet. We, by the way, used to call this entity resolution. Then, pretty soon, everybody used entity resolution for everything on the planet that has to do with record matching. And so we've had to change the name to entity-centric learning. I bring this out because it's taken years to perfect this. This was Gen 1. Most entity resolution technologies do record-to-record matching. That means when this record shows up, it has to find another record, not the union of the features. That turns out, I didn't realize it at the time, but incredibly important if you're dealing with missions where you have lower quality data, and especially bad guys that don't use the same name, address, and phone on every record. So this system, we developed entity-centric learning because you have hundreds of data sources. We developed a technique to create a standardized input. So we would take all the 100 different sources and bring them to a canonical form. We had to solve fuzzy matching like month and day transpose and date of birth. We needed to do name root dictionaries like Dick, Dickie, Richie, Ricardo, Elizabeth, and Beth. There's something called blocking methods. If you want something to scale and you get a new record, you got to go find some candidates. So we had some simple examples like first three letters of the last name plus the first name. And we didn't know of any other way, but we did batch entity resolution via transactional record processing. So every time a chunk would show up from a hospital with another 50 records in it, we would just incrementally add the 50 records. Okay, fast forward. Now we're in the early 90s, Gen 2. It became known as NORA, non-obvious relationship awareness. This is for Las Vegas casinos. And here, this was for a casino conglomerate, if you will, a chain, not a chain, but they owned a bunch of different casinos. Hotel, everyone making hotel reservations, everybody checking in, the loyalty club, casino credit, employees, terminated employees. They know your policies, they know your procedures, they know your people. And then they had 18 different kinds of watch lists. One example, maybe the biggest problem for them are these regulatory lists. I just checked, this person's still on there as of today, been on there for a long time. But you cannot transact with this person if you're a casino. This is like what the OFAC list is by the Department of Treasury. If you're a bank, you best not be transacting with these people. You'll lose your gaming license or you'll be heavily fined. In this use cases, they're trying to make sure that the people they're doing business with, vendors, players, people they're extending credit to, they don't even want to give free rooms to people on the exclusionary list. So they're trying to monitor all these data sources to make sure none of them show up. Now, they also have people who are problem gamblers and they self-express and say, don't market to me. So you want to make sure you're not accidentally marketing to them. And then you have card counters. By the way, we built the software to bring down the MIT card count team. So if you read the book, Bringing Down the House, or saw the movie 21, we built that too. So, and so there's like 10 million records. It's got people data and company data, dozens of good guy and bad guy data sets, the clever bad actors. Here you find out people are using 6 different names, 5 different social security numbers, 3 different dates of birth. It turns out in entity resolution, everything's an array. And then you have to see the graph. You have to see who's related to who. You want to find out if the dealer shares an address with somebody that's affiliated with persona non grata. And I dusted this off. Here's some original results from that first run. We found 24 people in their loyalty club who were known cheaters. One of them, they'd paid a first-class ticket to fly the cheater back. I remember briefing the head of security, showing them that, hey, look at this. You just bought somebody this plane ticket. He goes, are you telling me we're paying the cheaters to fly here? Okay. 23 of the people in the loyalty club had relationships, like a phone number, or they were the reference on an or a family or loved one, or they shared phone or address. 12 of the employees were in the loyalty club. That was against the rules at the time. 192 employees were related to the vendor, but more interestingly, 7 of the employees didn't know the vendor. They were the vendor. And so it's this technology here, by the way, that caught the eye of In-Q-Tel, the venture capital arm of the CIA. And they funded us a little seed round in 2001 because of its ability to find very clever people trying to really obfuscate who they are. And so what did we learn there? We ended up with, in this Gen 2, it was a more advanced database schemas, so you could combine more and more data sets without any schema change. We put names in a table, addresses in a table, phones in a table, IDs in a table, and so you could have an array of anything, unlimited numbers of IDs or phones, addresses, dates of birth. We generalized our input format a bit. We improved our data quality processes. We started doing relationship discovery. You're building the graph while the data lands. While you're doing your blocking factors to figure out who it might be. When you're done figuring out who's who, there's stuff left in your blocking factors. You're like, wow, why did I find that? Oh, the address was the same. Ha! I will cast a relationship. And then doing insight at ingestion. So as they're ingesting the data, it's producing tipping and queuing, helping focus human attention. Now, jump to Gen 3, a little later in the 90s, before the word big data. Boom. This company owned Ramada, Howard Johnson, Super 8, Days Inn, Nights Inn, Travelodge, Wingate, 23% of all the hotels in the US. And they owned Avis and Budget Rent-A-Car. And they owned Century 21, ERA, and Coldwell Banker. They had 5,000 data sources, a billion transactions, about 100 million people. This is in the 90s. And the purpose of this system was to understand who was who, so you could predict who was going to go to Orlando the first week of May. And if you knew Jeff Jonas was going to Orlando the first week of May, what you want to then ask yourself is, that Jeff Jonas guy, is he easier to influence 3 months before because he does long-term planning? Or is he of a whim kind of person that's going to make his reservations last minute? And that's what this Gen 3 did. So this is building 360-degree views across different kinds of brands. It's for targeted marketing. Here's the challenge is we started out with 4,200 data sources. While we're trying to take the plane off and build it, they ended up with 800 more. There's too many data sources to even inventory. It'd be like painting the Golden Gate Bridge. You get to one end. Imagine trying to inventory that many. By the time you get to one end, they're changing out versions. You can't first fix all the messy data. You can't first replace all the systems and make them compatible to the way you want it. You actually have to operate on the data at hand. And that this led to really deep things embedded in the way we have learned to build entity resolution that gives you the freedom of action to combine more data sets with almost effortless. Um, the other thing that happens is when you have different hotel chains and Avis and Budget Rent-A-Car and the real estate, all those different stakeholders have very different competing interests. You can't even have the conversation about which address shall be the main address. There's no such thing as that. Because the person with the loyalty club statement says, we're going to send it to them no matter what other information you have. That's where they said they want their loyalty statement to go. And so, in fact, that's the fourth bullet here on some of the techniques developed. We learned that you have to manage every version of truth. You have to have full attribution and full pedigree. And because when you bring the data to one group, I'll call it as a mart, a data mart, the structure that is for them and it's around their preferences and data survivorship or rules of visibility. So here, the other thing that we learned, this whole system came to a creaking halt as it was ingesting. It got to about 10 million of the billion records and started processing one record every 10 minutes because some data came from travel agencies, and travel agencies might have this phone number that's a generic toll-free number. And suddenly you have 500 people at the same number. Then you have 5,000 people that are at that number. And what historically you have to do is pre-train a system, learn all of those overly generic values. But what we learned is how to do that in real time so that while it's running, it discovers overused values, like phone numbers are pretty good, but not this one, and then use that as part of its real-time learning, which we've continued to develop. We also tried this thing with microservices, like this thing cleans the addresses, then there's a queue to this thing that fixes the phone number and a queue to this thing. What happens when you do that is you learn that you have a lot of queue maintenance, and it really brings a burden to the operational simplicity. One of the reasons why we're in SDK now. Now, late 90s, we called it ERIK. I know the ER is for entity resolution, but I forget what the IK means. It was our first commercial off-the-shelf technology, general purpose, was designed for good guy hunting or customer 360 at the same time in the same instance, real time with relationship awareness, continuous alerting at thousands of things a second. We combined everything we learned, low latency. We worked on making it more accurate and at scale. And there's a thing called drift. As you load new records, you might learn something that invalidates earlier decisions. Maybe you learned a new value, like a phone number that's generic, but did you fix all the past ones? Now you just learned somebody's middle name was P, but it's really Paul. Now that you know the middle name is Paul, would you have made any decisions differently? And as you explore this, we come to call it sequence neutrality. Did you learn A first, then B, then C? Or C first, then B, then A? Some people call it monotonic. Some people call it commutative. But we've used the word sequence neutrality. And so in Gen 4, as new records land, you have to reevaluate it to see if other records should collapse. And more expensive is you have to figure out if you've learned something that should cause other entities to explode. Doing that real time on streaming data is pretty tough. We got really good at full attribution here, and we built more improved kind of data quality management as the data is flowing through. Okay, now we're at Gen 5. This is IBM Identity Insight. IBM buys my company. And so In-Q-Tel funded us in 2001. In 2003, Reed Elsevier, parent of LexisNexis, funds our company in an A round. And we sell the Senzing entity resolution technology to IBM. It's still the product with IBM today. It's an amazing product. The team and I helped build it. It's like our oldest daughter. She's amazing. Um, but this is a widely sold now COTS product and industrial strength. And this class of technologies, it's a real-time engine for all these kind of use cases, n degrees of separation. Tell me how Billy knows Kenny, and it'll find all the paths. Real-time publishing scales beyond 100 billion input records, name, address, phone, all-purpose ingest format. So you can take any use case we've had, from tax offices to money service businesses to government counterterrorism programs, same schema. And we've solved better sequence neutrality at scale to even further reduce drift. And we got rid of all the dependencies on the database on triggers. At the end of the day, it's a shared information space, and you want to reduce the burden on the engine itself. And so we just stripped the engine of triggers and stored procedures, which means you can kind of run it more universally across an SQL backend. We need SQL for the ACID properties and the low latency. Better furball handling. A furball's when too many records start binding, and pretty soon you got 70,000 records all kind of plumped into one thing. We worked on one-way hashes, so you could this is used today in our work for over half of America's voter registration, where name and address are public record, but driver's license, date of birth, and social are not. And so before those move to be entity resolved, they're one-way hashed at the edge, salted twice, blah, blah. And we embedded global name recognition, which is some really amazing technology that IBM has, that understands the cultures of names and how to match them. And so now we're at 2009. The team and I, all still together, been doing this for a long time. We're at IBM. No one thinks I'm going to stay because I'm the largest shareholder, but I've been there for years. And I get asked, what would you do next? And I said, I'd like to start over from scratch. And it's going to cost $50 million. Because what happens is, I will tell you, when you build these engines over and over, it's easy to show progress. Everyone just starts and go, look, we're making progress. You assume progress will be linear, but progress is not linear. As you get closer to the top of the tree, it's shaped more and more like a needle, and it's covered with better and better grease and oil. And then you realize you got the wrong tools, and you have to start over and over. And so we did. We spent a year just on the schema, because structure governs function. And so now, so we build it, we start shipping it. G2, by the way, not for generation 2, but G for genus, species 2, because it's so radically different. But 11 and a half years in, I go to my boss at IBM. I give him a little matrix, red pill, blue pill. I said, I got to go. I want to go back to my entrepreneurial roots. Either you're going to let me spin it out, or I'm going to go build something in my garage and I'll see you in the market in a year. And they picked red pill. And so I will introduce to you now Senzing. This is where Senzing becomes born, is the rights to the intellectual property, rights to use some patents, rights for the code base that we build, the G2 code base. I got to bring my team out. We spin out in 2016. We go back into stealth mode, and we come out of stealth in 2018. We're about 30 people. Half our businesses is public sector government, and the other half is biggest banks, biggest healthcare, and so on. An entire purpose is to make entity resolution easy for developers, so people know who they're doing business with. And so about this Gen 6 engine, first of all, it's an SDK. Our emphasis in terms of use cases, people data and company data across languages, scaling beyond 100 billion records if you need it. So scale is not an issue for anyone. Cloud first, runs on bare metal, but I can run it on my laptop. Whole bunch of privacy features built in. Our goals was delivered. No one has figured out how to take this much work and reduce it to a linked library. No moving parts, no points of failure. Little universities use us and pay us $4,000 a year. It's no longer just for the elite. And the biggest organizations in the world, they pay an all-you-can-eat price. It's like about $1 million a year. So we've just really made it affordable. Out of the box, it's outperforming humans across missions and languages without training and tuning. You don't need experts anymore. It does continuous real-time learning was one of the other goals. It's 8 times easier to prepare the data. You don't have to clean the addresses. You don't have to parse the names. You don't have to sort out what the phone numbers are with the +65 for Singapore at the front. Horizontally scales. And most importantly, what's unique about our use of AI that does real-time learning while it's running is not Gen AI. It gives you the same answer every time, and it's explainable. Why are those records together or why not? And so when the techniques developed, we we broke out of rule-based systems, and I created this patent called principle-based entity resolution. No, not time to go through it right now, but it's a pluggable architecture. So if you wanted to create polygons of properties and compare the shapes of those to know if they could be the same properties, you could do it. Or you could do voice or face. We've done an app level encryption. So if you want to encrypt the data at the application level where even the DBA is corrupt, your data is not exposed, that's a plugin. Those feature statistics about generic now manage, they automatically run across all the features, and it's entirely self-optimizing as the statistics change. So it beats humans out of the box, and then it's self-tuning in real time and fixes the past. Super hard to do at thousands of records a second against billions of records. There's something called ambiguous. George Foreman named all 5 of his boys George Foreman. People, that means if you have George Foreman and a home address and a home phone, it could be any of them. Almost every other engine out there will randomly give. Oops, I have a high five. Great, good for me. Sorry. But if you get a George Foreman record, it'll randomly give it to one of the Georges. But Senzing notices that it can find it late and can fix it. One of the schema changes that we made, and I had to study it for a year, is just so you can change your mind about the past fast. We made it support double byte character sets. The stuff we're doing in Mandarin and Korean is really further distances us. And this full explainability, these function calls about why not, or how did this entity come to evolve, turns out to just be really important if you're making big decisions. So our use cases, as you might imagine, about 3/4 of our business turns out to be bad guy hunting. The remainder is like customer 360. And within those, you see this work that's being done about using entity resolved knowledge graphs, as Paco's going to cover, for RAG, for better machine learning to improve graph analytics, nearest neighbor, shortest path, centrality without entity resolution. What do you got? And so we find ourselves today being built into other people's things as an SDK. Nice Actimize, 95% of all banks, over 50 billion in assets. We're their engine. Verus, 95% of all insurance fraud claims. This one over here, over half of America's voter registration. And so here's how Senzing works in a nutshell. 3 or 4 minutes. Here we go. It's a developer library, just like why would you build your own spell checker? Really? Okay. That's where Senzing lives right there. Sits on top of a SQL database of your choice called the persistent entity graph. Input, search or add, name, address, phone, plus whatever, date of birth, company ID, blah. Output, same, possibly the same related. It's JSON in and JSON out. These resolved, tells you why with the match key. They resolved a name, address, and phone. The why will tell you the scores of each, what culture the name was, and within that culture, how did it score? And people are building us into their workflows with just a few lines of code. Create a JSON record with our little JSON standard format. That's the data source. That's the attribution, the record in that data source. That's the JSON record. Done. That handles all the change in mind about the past, fixes all the statistics, does the self-learning, blah, 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 all built into that one. And then you fetch the record, you go get the entity. It's all built in C++, multi-threaded, super high performance, ultra low latency. It's got wrappers for Python, Java, Go.NET. On the left side, people put in the historical data, new data, reference data, streaming data, batch data, and out the right, workflows, decisioning engine, visualizations, graph databases. They're dropping into Elasticsearch, putting into real-time workflows, warehouses, lakes. It's your stack. Inside that SDK, this are the steps. That's the JSON in, that's the JSON out. Each of these steps, the sprocket's configurable, the plug, you can plug your own in. The tens of millions of the 50 million has been invested right here. The next most expensive part is here. This is the most innovative part about why it does not need to be trained or tuned anymore. And you can add new data sources at a whim. But right here, I'm going to drill into compare features for a second. Inside of compare features, it has a pre-built, it has a variety of features, comparators, but one of them is social security numbers. It knows which socials were used in the 70s for advertising on billboards. The name comparator pre-trained on 850 million names. You can't do this with edit distance, my friends. These names are the same. These names are different. You better know the culture to do that across languages, across all these languages. Not too far long ago, we hired someone to do Burmese, a linguist to do Burmese and Cambodian. And since then, we've been continuing. Here it knows these addresses are exactly the same. If you have two businesses at the same address, you graph them. These addresses are different. If you can't do global worldwide address parsing, you can't solve this with simple string compares. And we do it across languages, and most recently in version 4, Mandarin, addresses, business names. Most people get us embedded in their systems with less than 10 calls: add, delete, get, search, find, and why. Companies like Linkurious build us in. Their config screen talks to the Senzing engine with JSON and produces graphs like that. Graph-aware Hume. This is what the graph looks like without entity resolution. That's what it looks like with. Here's I2 Analyst Notebook, very popular product on the desktop for investigations. That's an insurance fraud case. These are a bunch of orphaned. After entity resolution plus discovered relations, it looks like that. Utterly changes in investigation or graph analytics. Esri, ArcGIS Knowledge, PPP Loans, Las Vegas, a bunch of little orphans. After entity resolution, it looks like that. One person, three people, three loans, or one person, three loans. And so when you're visualizing it, it looks like that. Last chart. Boy, there's a lot of things you would want in entity resolution if you have a little wish list. This, that, this, that. You can read it as fast as I can say it. Guess what the hard part is? Making it easy. You have to start over and over and over to make it easy. By our estimation, I've checked with other entity resolution companies there's some appreciation of this, but if you wanted 70% of this, you could spend about $1 million. If you want to get 80% of this list, you're going to spend about $5 million trying to build this. If you want to get the 90% of this list, and that's not even competitive these days, you're going to spend 30 million. It is that hard, and you don't know it until you try to get closer and closer up the tree. And with that, my goal is 25 minutes. I'm 1 minute and 16 seconds over. Paco?
Wonderful. Um, Thank you very much. I appreciate getting to present here, and it's really fun to see a lot of familiar faces and names on the call, some friends I haven't seen in a while. My name is Paco Nathan. I'm DevRel on the engineering team, and some of you might know me through Graph community. Some of you might have known me through O'Reilly Media conferences, or I taught thousands of people how to use Apache Spark way back when. But I have a background in natural language, graph technologies, distributed systems. I made the mistake of going into artificial intelligence in grad school about 40 plus years ago. So next slide. This here, I love this quote from Abhishek Nagaraj at Berkeley. Think of data as an imperfect map of the underlying entities. Because so much when we're representing about people and companies and vessels and all, this is what we're doing over and over, is we're using data and we're having to navigate this kind of imperfect map. But another way of saying that is that within any collection of data set, there's going to be some nodes and some relations, probably some annotations, properties, etc. Identifying the non-obvious connections, as Jeff was talking about, this is really the core challenge and how we can leverage data. Next slide, please. Next slide. So when you take the output from entity resolution from Senzing, you're getting out of this a couple of lists for each entity. One is here are the records that we're pointing to, the data records that provide evidence. Here is why for each one, what probabilistically, what kind of strength is there. And here's also other entities that are close, they're related. We don't have enough evidence collected yet to say that we should merge these, but if you're doing an investigation, these would be your hot leads. And when you look at this, realistically, these are entities and relations and properties. And so entity resolution is providing this kind of semantic overlay, which is really building blocks for a graph. Next slide, please. And so I can imagine in this audience here, I know in several cases, but you're probably familiar with using tools like WordNet. I wanted to make the comparison because WordNet is a kind of programmatically accessible thesaurus. It's used a lot because you can leverage this for semantic expansions, random walks, entity linking, etc. There's a lot of things that we can do when we're working on graph applications leveraging a thesaurus. And to underscore that, next slide. There's a really great set of talks and articles by a friend, Jessica Talisman, and she's talking about development of mapping your data into ontologies, really thinking about the different components, the assets you'll be using in terms of controlled vocabularies, different thesaurus, different taxonomies, etc. And I want to underscore the part because Senzing, when you look at it from the perspective of developing graphs and leveraging graphs and downstream AI applications, Senzing is providing a kind of domain-specific thesaurus. And this can be used in many ways, partly for constructing graphs, but also for customizing entity linking, also for expanding if you're working in, say, GraphRag or agents. If you land on some nodes because of a query, can you expand out from there? Can you do a semantic random walk to link up what you found, but keep it within your domain without just searching randomly across the graph? So there's a lot of ways that you can really leverage what's going on with entity resolution in a graph context. Next slide, please. And I should also distinguish here, if you've done work in natural language, you've probably heard NER, named entity recognition. And I want to contrast these. NER is very, very different from ER, entity resolution. NER is where I have parsed some text, I have a noun phrase, I'm going to apply a label on the noun phrase, person, place, or thing. Entity resolution is where you're disambiguating, you're finding a footprint for consistent entities across data sets on structured data, typically operating on PII features. Now, there is something called entity linking, which really blends the two, where you can take entity resolution results from structured data and NER results from unstructured data and pull them together into a graph. So we like to think of entity resolution as providing a kind of backbone for organizing your graph and allowing for this kind of structuring to happen in a very consistent, robust kind of way that's domain specific. Next slide, please. And to take this further, my colleague Ben Lorica, a couple of years ago, wrote this industry report about modern entity resolution systems, what to consider, where the hard parts are. And again, it's echoing a lot of what Jeff just presented, but definitely a good read there. And along with that, there are several other case studies. Here's a recent one from Waihow, an AI company in San Francisco, turning congressional hearings into knowledge graphs and then operating on them. A lot of other different partners and vendors we've been working with, Kinaviz, GraphAware, Enterprise Knowledge, and others. Next slide, please. And so I want to go back to some of the slides that Jeff was showing about integrations, like with Blinkurious and GraphAware and other I2 and others. There's a typical kind of design pattern that we see. It's used in anti-fraud, but it's also used in customer 360 and marketing and these other kinds of use cases. So this is a typical pattern, 4 steps that we see either for looking for the worst criminals in your network or looking for your best customers. And the problem is this. Here I'm illustrating a couple of data sets. One is open sanctions, a risk data set, and one is open ownership, which is beneficial ownership. And if you just take the raw data already, it's connected. You're starting to get graphs, but they're kind of disconnected here. They're not fully connected. And these nodes and relations that I'm visualizing here, they're actually for a known fraud ring. It's about somebody named Abassine Badshaw, who was convicted of about £1 million of money laundering, tax evasion in London, had a chain of Papa John's. So the pattern is this. Use entity resolution and bring together the different data sources into a connected graph, create this kind of backbone for structuring your graph. And then step 2, typically some type of algorithmic partitioning like Louvain or weakly connected components, or other means of basically taking a very large graph, which might be billions of elements, and instead changing the aperture, narrowing the aperture so that you're looking at subgraphs of interest. Because when a fraud analyst is going to go use this data, this graph data, they need to be working at human scale, which is probably more like 20 nodes as opposed to 5 billion. Step 3, another graph algorithm you typically use is some type of centrality. So it might be degree centrality or betweenness centrality, different ways of understanding within my subgraph here, who's really orchestrating this? Who's the most connected person, or who's the real pivotal part that connects all these together? That's probably the person who's calling the shots. And then step 4, take these graph insights, run them through your case management tools, typically in a bank. And then as an analyst is pulling up, they're getting this kind of interactive visualization. I'll go to the next slide. Because by virtue of running entity resolution, all the parts connect together. And so now after you've done your partitioning and you do centrality analysis, now you can see in the center, just like with PageRank, this one central character, Abasin Badshaw, who actually was the ultimate beneficial owner for this fraud ring, he bubbles up to the top. Previously, he had not been as prominent, but now, because by virtue of running graph algorithms on this, now you can really get a clear view at human scale. Next slide, please. And so there's a couple of design patterns that get used together. We typically see working with entity resolution, building graphs, and then also handling updates. Typically, when you're initializing, you'll take a lot of data, run it through bulk processing. So we're kind of a sidecar to your ETL. You take your data records, you peel off your PI features, run those through entity resolution, get this kind of graph backbone. And it creates a kind of overlay on top of your data records in your graph. But then you're going to have data updates. And so now you want to get into more, not bulk processing, but more low latency streaming. And so as data deltas come in, data updates come in, peel off those PII features on the nodes that have been updated, run them through entity resolution, and they make a round trip. And now this will be telling you to either merge or split this kind of overlay that's organizing your data records, telling you that, okay, now we know that, Robert Smith and Bob Smith are the same person, or now we know that, Bob Smith Sr. and Bob Smith Jr. are different people because we've had new data come in. So again, organizing the graph. And then next slide, there's another kind of pattern that we're looking at, seeing more, where think of like a low latency streaming question and answer kind of deployment. You've got questions coming in, and maybe somebody is asking about Abu Badshaw, born on Jan 17, 1974. We can use tools like BAML or DSPy or whatever, but we can come out with the kind of JSON fragment that we were showing before, and now search, what do we know about this within the context of what we've done with entity resolution. From that, we get a subgraph, everything that we know about Abu, and sort of an audit trail to all the different shell companies, et cetera. And this could be running through a Gen AI service, which is basically GraphRag or some kind of agent similar to that, but consuming from the graph data and also incorporating other unstructured data, might be log transactions, events, wire transfers, other types of facts, but coming out with a Gen AI-based question and answer system. So that's another type of deployment pattern we see. Next slide, please. And there's excellent work here. We work with so many different data providers. Some of that is open data, but a lot of that is commercial data. So we've worked closely with some of the more popular data providers to make open slices for particular geo areas. So Vegas, London, Moscow. And we've got these collections of different data sets that if you want to build some interesting graphs, this is definitely a place to go. Check out the chord snapshots. Okay, next slide. And I want to drill into the patterns that we would typically see in something like GraphRag or agent workflows downstream. And this is kind of a generalized architecture just to give the idea, but typically you have a couple of workflows. You have your structured data sources, as I mentioned, and you peel off PII features, go through entity resolution, and you're building out your graph. And you also have other taxonomy, control vocabulary, et cetera, that's going into the construction of the graph. As you get updates, you get this cycle up at the top there where updates go back to entity resolution, and then you get updated merge or split decisions. At the bottom, unstructured data going through a RAG pipeline. You do your text chunking, you run it through your embedding model, drop it into your vector store. But you could also take the text from your unstructured data, parse it, use named entity recognition, as well as relation extraction and other NLP techniques to construct a lexical graph. And then part of the magic is you really want to tie together the elements from your graph store with the elements from your vector store to make the most out of leveraging them at runtime for AI applications. So this is where the idea of a thesaurus, a domain-specific thesaurus based on your structured data, comes in, because it not only helps to organize your graph, but it also can help to customize entity linking, which can tie together. I'll show an example of this later, but it can tie together what you're getting out of the unstructured data sources and the structured data sources, bringing them together to help you organize this. Okay, next slide, please. So then at runtime, a prompt comes in, it'll go a couple of directions. One direction, of course, through the embedding model and nearest neighbor search through the vector store to develop a list of chunks that you'll keep around and provide to the LLM later to generate a response. But the top line is where your prompt will go through some type of query or some type of embedding model on your nodes and edges, basically land in some short list of elements of your graph that are interesting, that are related to the prompt. And now the game is to be able to work back and forth between the vector elements and the graph elements that are connected together. Perhaps you might want to do expansions or semantic random walks to juice this up. And then run some type of graph algorithms at the end, as I was showing before. But at the end of the day, you're going to come out with a ranked index of chunks that are basically the fuel that you provide for the LLM to summarize. And so this is kind of a generalized view of what's happening with GraphRag, what's happening with agentic workflows, and where we see entity resolution playing a part in this. Next slide, please. And so there's some tutorials. Prashant Rao and I just did this tutorial at KGC, and I know that several people in the audience were actually in our tutorial. Thank you. We had a really great time with this, but we've got an open source project on GitHub that shows how to use Senzing and KuzuDB together to develop knowledge graphs, and then downstream, how you can use this for building agents, etc. We just had the first in a series of articles come out this week. We'll have another one coming out. We're doing some work with Weidong Yang from Kinaviz for further integration. And I think we'll probably be doing another version of this at Connected Data London too. Next slide, please. And then we've got a series of tutorials based on Neo4j, where we were looking at the PPP loan fraud that we'd mentioned a little bit earlier. This is using some US federal open data to understand where was there fraud instance or potential incidents in Las Vegas. Next slide, please. And so I did a tutorial working with both Senzing and Neo4j team, and that's up online on GitHub. My colleague Claire Sullivan took that and then added LangChain to show how to do GraphRag, how to do question and answer, AI applications downstream from this. And Claire and I have both been working on a series of other tutorials to extend this. Next slide. And then I've got a set of, well, it's an open source repo, but it's basically showing how to use state-of-the-art models for extracting entities and relations from unstructured data, and then blending that together to build a graph along with what you would do with Senzing to build out the backbone. So this is answering more about the unstructured data. And then to tie it together, next slide, one of our colleagues, Liu Guiton, recently did a tutorial about customizing the entity linking. And so here he took data from the Panama Papers, using Senzing entity resolution, using LanceDB, and built out a custom entity linker as a spacey pipeline. And so the next slide will illustrate this. Next slide, please. So here we've got part of the Azerbaijani laundromat. We've got some investigative journalism. We had already run through using open sanctions and open ownership, built out a graph describing the Azerbaijani laundromat. And so now with this entity linker, as we're parsing articles about that case, they are automatically being linked into the graph. And you can see wherever the purple rectangles are, those are actual identifiers in the graph that was previously created. So this is a way of doing very high quality domain specific blending of your structured data and your unstructured data within a graph. And then downstream, you could have Q&A, you could have agents, etc. Next slide, please. And taking this further, if you want to look at Azerbaijani laundromat, we have this online on GitHub, but it's taking the data from the Azerbaijani laundromat, which is like $3 billion of money laundering, and doing some forensic accounting and then some flow analysis in a temporal graph, understanding the kind of patterns of fraud tradecraft that are being employed for very large scale money laundering. And then from there, how can we get a visualization where these kinds of tradecraft graph patterns just pop right out? Next slide, please. And so just to wrap up, I definitely want to shout out, got some other friends here from Graph Geeks. I'm wearing my Graph Geeks shirt, but we have a study group at Graph Geeks about investigative graphs. We meet every couple of weeks and we have experts working in fraud and other areas come in and talk with us. A lot of interesting offshoots from this group and a lot more going on at Graph Geeks as well. And then next slide. And every month I do a webinar, live Q&A with audience. In fact, we have another one coming up next week with Stephen Ebbett Pew, who's an expert in beneficial ownership. But we've got a series of this going on where we're bringing in graph experts to discuss these issues related to entity resolution, because typically wherever we see entity resolution practices of scale, usually there's a graph practice that's closely adjacent. And that's it. Thank you very much. Next slide. Yeah. Questions?
Well, that's great. I will just say, in case anybody drops early, that Paco and I are always keen to answer any emails that come our way. So feel free to just shoot us a note anytime.